Hello, good evening, everyone. Welcome to our Institute of Global Professional. Thank you for joining. Thank you for all joining with us in and remain with us till the end. Our lovely audience. Today, I am your host for this evening, Salma, core volunteer and head of ambassador in IGP. Ladies and gentlemen, I am proud to be associated with IGP as a global member, and I feel honored and privileged to host this webinar. It is my delight to welcome you all to our Institution of Global Professional free webinar. Thank you all for joining us today in this marvelous evening, and it's my humble request and pleasure to all to stay with us till the end, for I am sure you will get some many takeaways and payoffs from this webinar. Each time you can like, comment in this webinar. Don't forget to tag, share, and mention your friends in the comment box. So let's work together and learn together. We believe that power is gained by sharing knowledge. Once again, I am Salma, core volunteer and head of ambassador of this IGP. Every day some new participant join with us, so I have to give little concept about IGP, Institute of Global Professional. Serve student and community teachers providing holistic social work and education for create a proficient generation. It is a leading online physical development institute with thousands of learners worldwide. We make it get at able to use for every knowledge seeker to originate personality more ambitious and more confident to face any circumstances and develop on skills. We are interested with international recognition. We organize our webinar, training, online, offline courses, etc. by best and trained speaker courses from all over the world to create a best learning platform for you all. Our mission is to empower people and enhance skill. We have already completed 255 webinars successfully. And we expect that you all got a little bit benefited in this personal and professional life. And we wish that you all are remaining with us in this long journey. Let me remind you all again that don't forget to tag, comment, and share, and mention your friends in the comment box because your attachment encourages us to do better and best service to our lovely audience. Our mission is to empower our youth to so stay with us by your support. I'm cordially welcoming you all. Today we are presenting the webinar 256 with two speakers, Joshua Lasanga and Warren Visaya, and the topic is statistics and probability. Now it is time to start our program. So with IGP's mantra, feed your skill. So please invite our first speaker, Warren Visaya. Hello, sir.
Hello, good evening. Hello. Thank you, Ma'am Ume Salma, and also thank you to Sir Kaushik Datta. Thank you very much for inviting us here at Institute of Global Professionals.
Thank you, sir. You can continue your piece or your presentation.
Yes, sir. Yes, ma'am. I'm going to share my screen now so that we may start our webinar.
Dear audience, don't forget to tag your friends, mention your tag, share, and comment your friends in this webinar. This
Slide already visible with on the platform, ma'am.
yes, sir.
So this is now the number 256. Actually, it's 256. Hello and good evening. Welcome to Institute of Global Professionals free international webinar number 256 entitled Statistics and Probability. Statistics and probability go hand in hand. They are related areas of mathematics which concern themselves with analyzing the relative frequency of events. Since probability deals with the predicting the likelihood of future events, statistics, on the other hand, involves the analysis of the frequency of past events. And tonight, I, Warren V. Gragasin, together with Sir Joshua Lansangan Evaristo, both all the way from the Philippines, will try our very best to uncover necessary requirements of statistics and probability. Within the limited time, we'll try our very best to share with you the knowledge and necessary skills if there are. And so brace yourselves and join us in the wonderful evening of statistics and probability. But before that, may I acknowledge first the Institute of Global Professionals, especially Ma'am Salma and Sir Kaushik Data, and the people behind this event's success. Allow me also to thank our ever supportive Dr. Nestor P. Nuesca, the Mathematics Supervisor of Region 3, Central Luzon, Philippines. We also have, of course, our loving father of our division, Dr. Ronaldo A. Pozon, Schools Division Superintendent, Schools Division of Tarlac Province, Philippines. And allow me to thank a mentor who never ceased to believe in our potentials, Dr. Maria Carmen P. Cuenco, the OIC Schools Division Superintendent of the City Schools Division of Tarlac, Philippines. Of course, may I thank, of course, acknowledge our hardworking supervisor and a confidante to all, a confidant, a friend, Sir Augusto L. Ballesteros, our mathematics supervisor, Schools Division of Tarlac Province, still in the Philippines. I would like also to acknowledge Sir Darwin L. Catolico, our diligent principal of Herono Western National High School, Herono Tarlac, Philippines. Of course, our encouraging and conscientious team leader who invests much in discovering and trusting our potentials, Sir Redentor B. Tabamo, the head teacher 3 of Benigno S. Aquino National High School, Concepcion, Tarlac, Philippines. Ma'am Rizalina S. Catolico, our head teacher from the Herono Western National High School, Herono Tarlac, Philippines. And Dr. Mary Jean R. Isla, Master Teacher 2 of the Herono Western National High School, Herono Tarlac, Philippines. Aside from them, allow me to thank you all, our viewers and our participants of this webinar. I would like to thank you in advance for joining us tonight. Please share the platform to other classmates, teachers, or other researchers who would like to join our seminar or webinar tonight. And please be reminded that you may actively participate through the comment box of our Facebook live streaming. And again, this is Warren V. Gragasin from the Philippines, and this is our session first for the statistics. The first question that comes to our mind is, why do we need to study statistics? Of course, these are the reasons. Data are everywhere. We need to study statistics because whenever we move, wherever we go, whatever we do, data are everywhere. From the social media, from the tests that we are taking up in schools, the distance traveled, the food preferences, bills, and other more things. Another reason why we need to study statistics is that statistics helps predict and makes many decisions that affect our lives. Another example for prediction is that the weather occurrences. Results of studies and statistics help us decide what to choose, what will gonna happen if I choose this or I choose that. Will it rain today? What will happen to the economy in the next 3 years? What will be the result of the election? Or what are the things do we need to prepare for the pandemic and even the education during the new normal? So since data are everywhere and statistics help us predict and makes many decisions, I believe we really need to at least, if not master statistics, at least uncover the necessary things to be able to go on in life. And it helps us make professional decisions in any of our chosen career, whatever your career is. For example, you are in the hospitality industry, you are going to predict or compute, calculate, estimate for how many guests will you be able to handle during the peak season, which is during December in the hospitality industry, or whatever career. For example, in business, in aeronautics and other fields. We cannot go away with statistics because statistics is everywhere. And to be able to understand what statistics is, we usually define it first. And for the definition, I prepared a mnemonics with the mnemonics COPAI or COPAI. Statistics is a branch of mathematics or the science of collecting, organizing, presenting, analyzing, and interpreting data to assist in making more effective decisions. Again, the COPAI stands for collecting, we gather data; organizing, we organize them; presenting, which will later be discussed how to present them and analyze, and as well as to interpret. Um, there is a common misconception about statistics. When we say statistics, people think that it is only a bunch of numbers. It is only a set of multiple data. But when we say statistics, it's not just numbers. We are having misconception on statistics as related to mathematics, which is only numbers. Statistics is not just number. We are talking of the interpretation, the analyzation. With this, language is also interrelated with statistics. And let's first unlock difficulties in statistics. These are the terminologies that are often being in vague or in ambiguous situation, but actually they are easy to understand. The first one is the population versus sample. Actually, I know that you have idea about population and sample, but to some, I guess we need to share it to be able to clearly understand what the population and the sample are. So let's start with population. Population is the entire set of individuals or objects of interest or the measurements obtained from all individuals or objects of interest. So, in short, population is the totality or the whole. On the other hand, sample is a portion or part of the population of interest. This means it is only a part of the whole. To clearly understand, here is an image. Population means the whole or all items, and the sample means the items selected from the population. So from the whole population of 30 cars, suppose we are studying 30 cars, we are just taking sixth out of 30 cars. So the capital letter N means the total number or the whole population of the cars. while the small letter n, which is 6, means that we are only taking a part of the whole, which is 6 cars only. Aside from population versus sample, we also have sampling. So we have, I'm sorry, it's just a part of this slide technicality. We have two types of sampling. So the first one is the non-probability sampling. The non-probability sampling, and the second one is the probability sampling. Let's talk first about the non-probability sampling, and it's already presented on the screen. There are four types of them. The first one is the convenience sampling. The second one is the purposive sampling. We also have the snowball sampling and the quota sampling. When we say non-probability sampling, we are talking of sometimes they call it the non-random sampling, and it is often referred as a bias sampling. Let's talk about it. Convenience sampling first. The convenience sampling, for example, let's talk about a survey which is taken inside a mall or along the road. So the researcher or the one who is conducting the study goes on a mall or along the road to take samples because he or she believes that the most convenient sample are available on a mall or along the road. So that is convenience sampling. But there is a risk in convenience sampling, which will be later on be tackled. Another one is the purposive or the judgmental sampling. When we say judgmental or purposive sampling, it is also called authoritative sampling. Why? Because it is based on researchers' knowledge. There is somehow a bias because the researcher has already a bunch of knowledge, or at least a part of the research that he is predicting already. For example, let's have example of a university survey. Suppose we are taking a university survey. To avoid the result to be skewed, the researcher avoids those who are biased to the university. So instead of taking the answer or the opinion of the people who are biased to the university, or let's say against the university, he the researcher is omitting those who are biased to the university, which is also bias. He is omitting the bias against the university, but he is conducting a survey which is somehow in turning to be biased one. Or he is also omitting or avoiding the fanatics of the university or those who are pro universities. He or she only chose samples or the professor who is fair to the best of his knowledge. But what is bias there? The bias there is that for him, the professor he chose are the fair professors or the fair samples. However, it is subjective to his own knowledge and his own feelings only. So purposive samplings sometimes is risky. So that is the first one, convenience. The second one, purposive sampling. We also have the snowball sampling. The snowball sampling comes from the idea of a snowball. A snowball, when it rolls on the ground, it becomes bigger and bigger because it collects it collects snow from the ground as it rolls by. So the idea in this sampling is that this is often used to topics which are very sensitive and sometimes socially relevant but very sensitive topics like HIV, drug related topics or issues, child molestation, child rights, and other sensitive topics or issues. So snowball is used with this. How snowball is used as a sampling method? As a researcher, for example, I will find someone who is related or who is knowledgeable of the things that I want to study. For example, a social worker. And this social worker will in turn help me to find people who might I interview or who might help me find the answers to my questions. So that is the snowball. You are connecting people to the main target that we are hoping to interview or to get answers from. And the last but not the least, among the non-probability sampling, the non-probability sampling last example is the quota sampling. When we say quota sampling, we are talking only of limited number of people based on your decision. For example, I will only conduct study with individuals with specific traits like two, 250 males and 250 females. So that is based on my decision. 350 employed, 150 unemployed. And nesting from this 150 unemployed, I will also select 100 students from this unemployed. So if we will take a look at the quota sampling, the decision or the subjective part of the researcher is still there. So all of this for the convenience, the purposive, the snowball, and the quota sampling, these are non-probability sampling. These are somehow biased. But why do we need to present this? If this is bias, why do we need to study this? And when can I use this? Will I be able to use this? The answer is still yes. We will still be able to use them. How? So non-probability sampling is used first to create a hypothesis. Researchers use the non-probability sampling method to create an assumption when limited to no prior information is available. This method helps with the immediate return of data and builds a base for further research. Non-probability sampling is also used for exploratory research. Researchers use this sampling technique widely when conducting qualitative research, pilot studies, or exploratory research. This is often used with case studies, action researches that are qualitative, and for example, I want to study about malnutrition or ADHD, for example, those students who are under attention deficit hyperactivity or the ADHD. Of course, I will, if I want to study about ADHD, I will go to a person, to a certain person, or linkages or connections that will lead me to the people who are related to ADHD. I will not go to random sampling because I might get lost with my study if I will do that. And the last but not the least reason, budget and time constraints. It helps us minimize the expenses and the time constraints. As I've said, if I want to study about, for example, prostitution, HIV, and sensitive topics, of course, I will not risk myself to study the whole population of the Philippines or the whole population of Bangladesh. I will only select um, samples that maybe part of the snowball sampling or others non-random sampling that I will be using. So that will minimize the risk of spending too much money and spending too much time. So that is the advantage of non-probability. However, we have the probability sampling, which is more advisable. So from the probability sampling, we have still four examples. The first one is the simple random sampling. The second one is the systematic sampling. We also have stratified sampling. And the last one is cluster sampling. When we talk about simple random sampling, the idea is very simple. It's like the fishbowl or the raffle draw. The fishbowl or the raffle draw idea. So in a fishbowl, you will be only putting the names of 100 population, for example, 500 population, and then you will only pick the names of the people you will be gathering data from. Or in a raffle, for example, you will only cut strips of papers or prepare balls and put it on a raffle machine, and then you will be able to pick random samples from there. So that is non-biased. You are giving equal chance to everybody to be part of the study. The second one is the systematic sampling. When we say systematic sampling, we are picking samples with a system of counting with nth term. Nth term, or for example, the fifth term on every fifth household. So for example, I am going to every houses, so I will be picking only the fifth house to to take the survey or an interview. So that is how systematic sampling works. If you are not happy with your fifth term, maybe you are deciding from the 10th term, 100th term, if you are talking of a very large population, but it's usually on the 10th term, 5th term. That is how systematic sampling works. Another one is stratified sampling. When we say stratified sampling, it came from the word strata, which means there are groups of people, they are grouped together with the same characteristics. Example of this is the characteristics of the first strata is 17 and below. So you will be grouping the people from 17 and below. That's the first group. The second group is 18 to 25 years old. And the last group will be 26 and above. So there will be three strata, and in every strata, you will be sampling from them. And last but not the least is the cluster sample. Cluster sample is somehow similar with the stratified sampling because you are grouping people. But the difference is that in cluster sampling, they are divided, for example, according to area. In the United States, uh, the United States is divided into states. So you will be picking equal chances, equal number of samples from each state. In the Philippines, for example, we have from region 1 to region to other regions, to Cordillera region, to Central Luzon, to National Capital Region, and other regions. You will be taking a part of them which is equally divided. So that is the idea of cluster sampling. So those are the types of probability sampling. And with the types of probability sampling, the question again is, um, what is the advantage of probability sampling from the non-probability sampling? Of course, as I've said earlier, it reduces sample bias. Unlike in non-probability, the subjective part or the idea or the feeling, the knowledge of the researcher is already there, and it is authoritative. However, in non-probability, you are not going to control your samples because you are using this method to give equal chance to everybody. Another advantage is that since this is a probability sampling, therefore there will be diverse population. Since you did not pick the samples, you will be encountering a diverse set of population. And the last one is it creates an accurate sample. So most probably the result of your study will be the actual result of the whole population. So another question is that why do we need to have sampling? We need to do the sampling method because the methods, whatever method you use, because, for example, I'm going to take a survey in the whole country, in the Philippines. Will I ever make it on time? How many years will I take it to study the whole Philippines? So, for example, we have 120 million population. We will only take a part of the 120 million population to study to for the convenience of time and for the convenience of expenses. So those are the two types of samples. And another one to unlock is the parameter versus statistic. When we say parameter, a descriptive measure of computed from an entire population. So taken from an entire population, this parameter is a descriptive measure. On the other hand, a descriptive measure on sample is the so-called statistic. So the only difference between parameter and statistic is that it is taken from an entire population, and the other one, the statistic, is taken from a sample data only. So from our example earlier, with a population of 30 cars, we only pick 6 samples, which is 6 cars. Therefore, the parameter or the measurement to be used, for example, are the mean, the standard deviation, the correlation for the parameter. For the parameter, we have the symbol mu, sigma, or rho. We are using Greek letters for the population when we are measuring the population. And when we are measuring the sample or the statistic, we have the X bar, the S, and the R, which means we are using English letters, alphabets. On the other hand, the parameter uses Greek letters or alphabets. Next, to unlock, aside from parameter, aside from the population, statistic, and sample, we have the variable versus data. It is often a question whether we need to debate on the difference of variable and data, because there are people who claims that variable is also data. Actually, there are most of statisticians or most of mathematicians consider variable also as data, but there is a unique difference among them. So the first one is variable is quantity or characteristics which can vary from one individual to another. For example of this, later on we will give an example. Data, on the other hand, is the actual value of the variable. But whenever we are talking of our studies, it's often intertwined or often related or considered the same. The variable is considered the same way as the data, which is actually these are the variables. When we are talking of what is the average speed of 12 cars, for example, the variable is the speed, and the data taken from them are the following. For example, 60 kilometer per hour from a data set of 57 kilometer per hour, or 58, 59, 60, 60, 60, and so on. So that is the only unique difference between variable and data. But somehow, in most of the studies, we talk about data as variable and we talk about variable as data. And it doesn't matter. It's okay. It's okay. There's no problem with that. We are still conducting our study and we still understand what we are conducting. So there's no problem with it. Next, we have the classification of variables. Based on the nature of data, we have first categorical or the qualitative and numerical the quantitative. Of course, from the word numerical or quantity, this talks about number, and categorical or quality, this talks about words or nominal and ordinal. On the other hand, when we say numerical, these are the discrete and the continuous. So these are the four types of variable data, categories of data based on the nature of the data. When we talk of nominal data, for example, we talk about what vaccine do Asians prefer. So these the data to be taken are nominal because they are words, probably alphanumeric. Pwede din po. It's still okay. We use word with numbers. For example, the plate numbers of the cars, the student number, which is combined with letter and number. What vaccine do Asians prefer? We have Sinovac, Pfizer, J&J, Moderna, AstraZeneca. All of these are nominal data. These are nominal data. On the other hand, nominal data can be dichotomic or polynomic. When we say dichotomic, there are only two options. And for example, we have gender. When we talk about gender, we have masculine and feminine, or masculinity or femininity. When we talk about sex, since that is biological, we have male and female. But when we talk about gender, masculine or feminine only, because of the social issues, we are choosing gender as more preferred variable or data rather than sex. Polynomic, on the other hand, example from the word poly, which means many. Education, for example, we have three options: elementary, secondary, tertiary. In the Philippines, that is the type of education. I don't know whatever the divisions of the educational sector in other countries, but in the Philippines, it is usually identified as elementary, secondary, or tertiary. So polynomic means many. Dichotomic means there are only two options. Ordinal. The ordinal data answers this example question. What is the degree of protection in human after the vaccination? Degree of protection. And here are the ordinal statements or the data. We have absolute, moderate, slight, none. These are only examples. We may also use other other degrees of measurement such as highly effective, effective, moderately effective, less effective, ineffective, or other more terms. Let's move on to numerical data, which is the discrete. Example of this is how many vaccination shots do an Asian, I'm sorry, that is do an Asian only, or do Asians receive? I'm sorry for the typographical error. And the answers are 0, 1, 2, 3, 4, which are countable, whole numbers only. And in continuous data, when we say continuous data, these are the data that are measured with the importance of the decimal points or the um, continuity of numbers between each interval. So, what was the temperature when you were checked before the vaccination? For example, 36.14, 37.07, and so on. When we measure the height of a basketball player, for example, that is considered continuous data. Why? Because what is your height? Often we answer what is your height. The answer is, for example, your answer is 5'7". But that is not a whole number. When we talk about meters, centimeters, that is considered 7.2 meters. That's how we measure things. And measurement is considered continuous data. Another classification of data is based on the source of data. That is whether it is from a primary source or from a secondary source. When we say primary sources, these are the first hand data, which means the researcher itself or you yourself um, are taking the data from the samples through interview, survey, observation, or other methods of data gathering. So you yourself has the first hand data. On the secondary, um, we have, example, the journals, the published and the unpublished researches, theses, and dissertations, news from legitimate sources, of course, not from the fake news. Not so we should know how to eliminate fake news from the legitimate ones. And two types of statistics. We have descriptive and inferential. Again, since we only have limited time for tonight, I guess if the IGP will give us another chance to talk about statistics later on, we will exploring it more to more topics of inferential and descriptive statistics. However, tonight we'll try our very best to differentiate the two. When we talk about descriptive, methods of organizing, summarizing, and presenting data in an informative way. In short, it only describes the data. It only describes the data or the target population. Inferential, on the other hand, methods for using sample data to make general conclusions, inferences about the populations, and in other words, it gives or it arrives at an inference, judgment, a conclusion. So these are the differences of the two. The descriptive statistics analyzes data that helps describe, show, and summarize data under study. It also organize, analyze, and present data in meaningful way through graphs and other charts and tables, which will be later on discussed. It is used to describe a situation. It explains already known data and limited to a sample or population having small size. The types of measurement are the measure of central tendency, the mean median mode, and the measures of variability, the range, variance, and the standard deviation. The results are shown with the help of charts, graphs, and tables, which will be later on be presented. On the other hand, when we talk about inferential, it is the analysis of random sample of data taken from a population to describe and make inference about the population. It compares the tests, it tests, and predicts data. It is used to explain the chance of occurrences of events. It attempts to reach the conclusion about the population, the important difference, the quality that divides descriptive and inferential is that when we say descriptive, We are only describing the data. And when we say inferential, we are giving conclusion or inference, a judgment based on the data taken. Types, estimation of parameters, and testing of hypotheses, and results are shown with help of probability scores. We will further understand these two branches with the examples on the next slides. When we talk about descriptive statistics, we are like cops. We are like investigators. We are giving these mnemonics to clearly understand what descriptive statistics is. CUPS stands for collect data, present data, and summarize data. So when we collect data, it could be through primary and secondary sources. It can be through survey, interview, observation, readings. When we say present data, we are using tables, graphs, or charts. And last but not the least, we summarize data. Again, we only summarize data to present it to be able to understand and to be able to describe. But we are not making judgment or conclusion. So the summary of the data can be presented through central of tendency, distribution or dispersion, or the also called CSS, or the center shape and spread. How to collect data? The collection of data that are relevant to the problem being studied is commonly the most difficult part of descriptive statistics. It is the most difficult, most expensive, and time-consuming part of this entire study. Yes, that's true, because after collecting data, after your surveys, your interviews, after your travels, after your observations, we will be able to present the data at home only. You may be able to work in an office or at home only, while during the collection of data, you are moving from places to places and spending much money and time. Statistical data are usually obtained by counting. So when we say counting, these are the discrete data or variables, or measuring, this pertains to continuous variables or data. So that's it. A collection of data can be qualitative and quantitative, as we already defined earlier. Examples of qualitative or categorical data are hair color, ethnic groups, and other attributes of the population which are nominal and ordinal only. On the other hand, quantitative or numerical talks about the distance traveled to college. So we are talking about number, distance, measurement, number of children in the family, for example, and other more examples that are numerical. There are four levels of measurement. Again, it's nominal, ordinal, and the two new ones, the interval and the ratio. Nominal in no logical order and have no particular relationship. If we talk about nominal and ordinal, they are both category. They are both qualitative. However, the only difference between nominal and ordinal is that nominal doesn't pertain to any order. Just names, just category, just characteristics. No need for order. It's said to be mutually exclusive since an individual object or measurement can be included only one of them. Examples are gender, marital status, and the measure of central tendency that we are using here is the mode. Later on, we'll talk about the mode. But what for those who know what mode is, congratulations and thank you for still joining us, because later on we will still discuss a little bit preview of the mode. On the other hand, ordinal is also a categorical or qualitative data, but the distinction to nominal is that Order is implied or order is needed. Values in one category are larger or smaller than values in other categories. Example, rating, excellent, good, fair, or poor. So those are, I already have given another example earlier, efficient, less efficient, um, highly efficient, and other categorical data which are in an orderly manner. Next is interval. When we say interval, examples of interval are tenure. No, example of ordinal is still ordinal. Examples of these are tenure, position, and the Likert scale, of course, the famous Likert scale. And the measure of central tendency to be used is the median and the mode. Now is the interval. So these are the famous interval. In Likert scale, these are the famous interval. We have the 3-point interval. For example, 2.33 to 3.00, 1.67 to 2.32, 1.00 to 1.66. If that is 3-point interval, you may also use 4-point interval, or you may also use 5-point interval. And this is the most oftenly used intervals in Likert scale. Again, that is under interval. Under interval. Interval is set of numerical measurements in which the distance between numbers is of known constant size. Example, average handle time, AHT, temperature, IQ score, Lebron's height. Measure of central tendency to be used is mean, median, and mode. And last but not the least is ratio. When we talk about ratio, numerical measurements where the distance between the numbers is of a known constant size. In addition, there is a non-arbitrary 0 point. So in ratio, we are talking of the importance of zero. Zero. Unlike in interval, we are talking of the importance of the numbers in between, like the decimal numbers. In ratio, the importance of zero is also there. Examples of these are test scores, basketball scores, number of attendance, word count. And the measure of central tendency to be used, the mean, median, and the mode. So these are the levels of measurement. And I guess we know the differences in nominal, the ordinal, the interval, and the ratio. Descriptive statistics also talk about the presentation of data. So from the COPS, we are done with the collection or gathering data. After collecting and gathering data, we now present the data through tables, charts, or graphs. Presentation of qualitative data. Another example, when we talk about qualitative data, this can be presented using pivot table. Pivot table is a statistics tool that summarizes and reorganizes selective columns and rows of data in a spreadsheet or database table to obtain a desired report. It does not actually change the spreadsheet or database itself. It simply pivots or turns the data to view it from different perspective. An example of qualitative data is presented on the right side, and we have the available resources for distance learning. For example, smartphone, desktop, laptop, tablet, TV, radio. These are the variables. And the responses of the samples for personal, yes, no, no, and so on. So this is an example of pivot table which is used to present qualitative data. Next is contingency table. So later on, let's differentiate what is a pivot table and contingency table. This is also used for qualitative data. Contingency table is a table showing the distribution of one variable in rows and another in columns, used to study the association between the two variables. Observe the example below. Take a look at the last column, the fourth column with totals, all high learners, all middle learners, all low learners, all of our samples, of our sample. And below the last the last row is totals, all men, all women. So this is an example of contingency table wherein the rows and the columns has something to say. It is presented in this way because the association is important. Unlike in pivot table, um, it's just a symbol table that we are usually seeing or often observe in most of studies. But this is also used in most studies, the contingency table, if we are presenting association of two variables. This is another example of contingency table because on the right side, the last column and the last row has something to say. How about presentation of quantitative data? Qualitative data earlier, now we are talking of quantitative data or the numbers, the numerical data. So a very good example of presentation of quantitative data is through frequency table. It shows the frequency or number of occurrences in each of several categories. Frequency distributions are used to summarize large volumes of data values. So this is an example of frequency table wherein the previous ownership, we are talking of these variables, previous ownership of computer software. The the first one is the window none, the Windows, the Mac, and the total. The frequency or the number of ownership is 85, 60, 355, and the total. And on the other side is the relative frequency. In most studies, this simple frequency table can be seen, and this is relevant to most quantitative studies. We have the relative frequency, which can be computed from the frequency, which is on the next slide. This is another example. So the relative frequency, for example, the frequency is 1, 0, 2, 1, 2, and 4, a total of a sample of 10. Again, for a small letter, it's a sample of 10. The relative frequency can be computed by dividing the frequency with the total number of the sample, which is 10. So 1 divided by 10 is 0.10. 0 divided by 10 is 0. 2 divided by 10 is 0.20. 1 divided by 10 again is 0.10. 2 divided by 10 is 0.20. And 4 divided by 10 is 0.40. Of course, as the total of the relative frequency is always 1. On the other side, this can be seen also in most studies. Aside from relative frequency, percentage frequency is also presented. So when we talk about percentage, it's all about 100 parts, percent, percentum. From the word percentum, which means 100 parts. So we are only multiplying our relative frequency by 100. And the total should be 100 below. So that is 10, 0, 20, 10, 20, 40, and of course 100, a total of 100%. These are samples of presentation of quantitative data, which are often and relevant presentation to most studies. This is another example, cumulative frequency table, wherein if you take a look at this side on the first column, the marks. When we say the marks or the class marks, there is a class interval from 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60. We are using marks, class intervals or class marks when we are grouping data. We have grouped data when the data are um, too large. Unlike when we are using only 1 to 30 samples, when you are using hundreds, for this example, we are using 50 sample, we may group them or mark them, put them into class intervals. So from 0 to 10, there are 2 students, um, which means this is the frequency. From 10 to 20, there are 7, 15, 10, 11, 5, a total of 50. If you take a look, that is a capital letter N, which means that this is that whole population. And the cumulative frequency is taken from, we obtain first the first data, which is the 2, the value of 2, 2, then we add the next frequency. So that is 2 plus 7, and that is 9. 2 plus 7 is 9. 9 plus 15 is 24. So we are moving cumulative. 24 plus 10, that is 34. 34 plus 11, that is 45. 45 plus 5 is 50. The last part of the cumulative frequency is similar to the number of population. That is also 50. So this is another presentation of table. So let's have example of a frequency distribution with the data. How many data do we have? We have 185, 303, and so on. 1, 2, 3, 4, 5. We have a data of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 50. A data of 50. The first step in creating a cumulative frequency is that we should get the range. And range can be computed using this formula. Range is equal to the maximum value minus the minimum, the highest minus the lowest. The highest number is 340 and the lowest is 180. So subtracting them, we get 160. The range is 160. Step 2, determine the number of classes. So to get the number of classes, we have the formula m equals square root of n. So m equals square root of n is equal to 7.071 or approximately 7 classes. 7 classes. Next, step 3, determine the size of each classes. So the size of each classes can be computed by this formula. H equals the maximum minus minimum over M. If we take a look of the maximum minus minimum, this is also same with the range. So class size is equal to range over M. And our M earlier is 7. So the class size is 160. The range is 160 divided by 7, and that is 22.857, or approximately the class size should be 23. So we have now range, number of classes, and the class size. We may be able to create a table, frequency table. So let's start with the range. The range is 160. The number of classes is 7. There should be 7 classes. Let's count if there are 7 classes. There are 7 classes starting from the lowest mark, which is 180, and ending with the highest mark, which is 340. From this table, we started below 180 to 202. 203 to 225, 226 to 248, 249 to 271, 272 to 294, 295 to 317, 318 to 340, and there are seven class marks. How do I know what is the class size? We are already computed it earlier, and that is 23. So in between 180 and 202, there are 23 values, including 180 and 202. This can be presented from bottom to the top part of the table, or you may start at the top part or to the bottom, going down. So with the class mark, we often count the number of values between each class marks. For example, from top to bottom, we have 180 to 219, 220 to 259, 260 to 299, 300 to 340. You might ask, what is the difference of this frequency table from the earlier one? This is the frequency table that we constructed based on the rules. And this is the correct one. However, this one is not wrong also. This is also a correct table. Why? Um, this in statistics, there is no specific rule that tells us that we are wrong or correct unless we are manipulating the data. If we are manipulating the data, therefore that's already considered a no-no or a wrong one. But in this example, for example, in biostatistics, they are often using 40 as interval. So from 300 to 340, there are 40 interval. From 260 to 299, there are also 40 interval. They are using most of the time with 40 interval in biostatistics. In other studies, they prefer a number of 5 intervals or 10 intervals in most cases. But again, the correct process is what we discussed earlier, and this is the correct one. But we may also use the other statistical methods presented in many books. There are many books to be considered, but I have presented you the right process earlier. Moving on. So when we have the tally mark or the tallying, if we are tallying, we are just crossing out the values. For example, between 180 to 219, we have only 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So that the frequency is 9 between 180 to 219. And between 220 to 255, 59, we do the same process. We cross out the values or whatever you want. You encircle it, you wipe it out with whitewash or correction error tape, you highlight it with a marker. It's okay as long as you are counting the number of frequency correctly. So this is an example of the frequency distribution. The We present the frequency distribution with this style. Table 1, of course, the title. The title can be presented above the frequency table or below the frequency table. For this example, it's above. Table 1, frequency distribution of word counts in a typing test. So this is the frequency distribution, and I presented it with a class interval of 40. Frequency on the second column, and on the third column is the relative frequency. Again, the sum of the relative frequency is always 1. Below the table can be the footnotes or other notes that you may want to put it there. For example, the source of data, if it is taken from a secondary source. You may put the source of data, standard typing test of Verona Western National High School. Again, we are putting the source of data if it is taken from secondary sources. But if it is taken from primary source, which means the researcher has taken the data firsthand, therefore no need to put the source of data. And we now have graphical representation. Aside from tables, we also have graphical representation. And the advantages of graphical representation is that data are presented pictorially, it gives better insight and understanding of data, makes the presentation eye-catching, of course. When we are looking too much of words and numbers, there are people, because of individual differences, there are people or students or readers of your study who hates much or bunch of words, bunch of numbers. That is why we need sometimes to present it in a matter of graphics or a presentation of charts, because it is more eye catching and it is clearer, more clear. The data are presented pictorially and it's more clear. Example is the bar diagram. The first one is the bar diagram, which is most commonly used graphics. It is used to present nominal and ordinal scaled data. So bar graph is often used for nominal and ordinal scale data. For example, we have the variables red, green, blue, and yellow. So with these variables, we have the data. For red, we have 12 responses. From the data variable green, we have 8, blue, we have 8, and yellow, we have 4. Observe that there are spaces in between, because diagram really gives spaces to tell us that these are separate nominal or ordinal datas or variables. Again, the spaces matters because the bar diagram tells us that the nominal data or ordinal data are separated from each other. Unlike the next one is it's still bar. So these are the types of bar graph or chart diagram, bar chart or bar diagram. We have the simple one and the multi-bar. There are many bars. We have this example, the horizontal bar and the percentage bar. Histogram. This is the seemingly similar with the bar diagram. The histogram is the most frequently used graphical presentation of, take note of that, interval and ratio data. This time, there are no spaces in between. Again, it looks like the bar diagram, but there are no spaces in between. Why? Because the the lack of spaces in histogram means that there is continuity of the data, of the variable. So from 20 to 30, then the next one is 30 to 40, 40 to 50, 50 to 60. There is continuity, and this is advisable for interval and ratio scales. Unlike the bar graph, it's advisable for nominal and ordinal, which are categorical data. The importance of histogram. What is good with histogram is that when you're looking at the histogram itself, you may induce if the distribution is already normal or positively skewed or negatively skewed. So these are the importance of histogram. Area of blocks in histogram clearly shows the frequency of each class. Histograms show the spread of observation, uniformly spread or randomly spread, or showing central tendency. It provides information about skewness or symmetry of data. Provided with the examples below, the histogram can be determined. can determine if the distribution is normal, if the distribution is symmetrical, or if it is skewed. Next is frequency polygon. It aims to compare other distributions which provide a good summary of the data. So an example of frequency polygon is on the right side, and it is advisable for interval and ratio scales also. Good representation for interval and ratio scale. Uh, they are using midpoint of the class with this graphical representation from the mark class. Take a look at the table on the left side. From the mark or the class interval or class marks of 0.5 to 9.5, the midpoint of class is 5.0. The midpoint or the median of 0.5 to 9.5 is 5.0. And take a look at the graph on the right side. This type of graph is using the midpoint. So from 0 to 3, that is 5. The class mark of 5. We also have 14.5. We also have 24.5, 34.5, and so on. They are using the midpoint of class to present this type of graph. Another one is the ogive. An ogive is a cumulative frequency graph and is used to determine observations that lie above or below a certain value in a distribution. This is an example of ogive. Again, it is cumulative. Cumulative. Therefore, this type of chart or graph uses cumulative frequency, which I discussed earlier on how to compute for the cumulative frequency. So that is ogive. When we say ogive, it is a chart using cumulative frequency. We can calculate median from a less than ogive by using the summation of f over 2, or the summation of f divided by 2 to get the median. Next is the pie chart. The pie chart is very famous to us even when we were young. It displays the percentage breakdown of data by category and is used to emphasize relative sizes of the data components. It is advisable for nominal and ordinal scale. Take note of that, nominal and ordinal scale. For example, is uh, a pie chart of expenditures of funds from iTrex company. It is divided with wages, raw materials, shipping, overhead, and miscellaneous. And looking at the chart without any numbers, you may observe or interpret that the most of the expenses are coming from the miscellaneous and the shipping. The miscellaneous, that is similar to the color of miscellaneous expenses, followed by the raw materials and the shipping. So next one is the time series graph. The time series graph is a graph of data that have been measured over time. So that the time continuity here is very important. For example, this is a time series graph from 1981 to 1988. So from 1981 to 1988, there are certain points of data presented. So between 5 and 10 during the 1981 and so on. The Stanley Plot. The Stanley Plot is another presentation which is seemingly combination of table and a graph. I personally love this presentation of descriptive statistics because it's a combination of number and it also looks like a graph which is eye-catching because the numbers presented on the stem leaf is showing us a normal curve, a skewed curve, or a graph that is like the histogram. It can immediately determine median, mode, outliers, and skewness. So that is why I love Stanley Plot the most. But I often also use bar graph, histograms, and of course the pie chart. This is an example of stem leaf plot. So we have, instead of writing 20, so the values from that are under 20, we have 2 here stands for 20, 3 here stands for 30. So this means that under 30, we have datas as 3 and 0, 30, 3 and 2, 32, 3 and 5, 35. So this means that under 30, we have 3 observe, observable data. And in 44, we have 41, another 41, 43, 4 and 7 is 47, 4 and 8 is 48, and so on. We have 5 and 1 is 51, 5 and 3 is 53, 5 and another 3 is 53, 5 and 4 is 54, 56, 57, 58, 58, 58, 9. So that is how stem leaf plot looks like. And if you will rotate the stem leaf, you may observe that there is a graph. It seems like a bell curve, a normal distribution curve. And looking at it, you may also observe the median and the mode already without even computing it. But let's talk about that later, the median and the mode. So we are done with the presentation of data. Again, COPS stands for collect the data, check, present the data for P, check, and last but not the least is to summarize the data. So we are about to summarize the data we took. In summarizing data, we are talking about the center, shape, and spread. So don't forget the CSS, the center, shape, and spread. This entails the measure of central tendency, the distribution, and the measures of dispersion. When we talk about center, mean, median, and mode, these are the 3 important things to remember when we talk about the center. The first one is the mean, which is also known as the average. And I do believe we know how to compute average. It's just adding all the values divided by the total number of data. So from the population, the formula is mu equals summation of x over a capital letter N. And for the sample, we have the x bar equals summation of x over small letter n. But the shortcut there is that let's just remember to add all the data divided by the number of data. For example, calculate the average number of truck shipments from Bangladesh to Philippine cities for the following data given in thousands of bags. The first city is Tarlac, which is 67.0. In Cebu, we have 15.0. In Baguio, we have 75.0. Davao, we have 68.0. And in Pasig, we have 67.0. So we just need to add all the values. That is 64 plus 15 plus 285 plus 228 plus 45 divided by 5. And the mean of the population is 127.4. 127.4. Next is median. So again, the mean is average. On the other side, median is the middle term. It is commonly used with the symbol M or MD or med or for median, or the X with a tilde. It's not X bar, it's X with a tilde. And in getting the median, the first rule is to arrange the data from least to greatest or vice versa. For 2.A, if you already arrange the data, consider if the data is odd or even. If if the data of the set of numbers is odd, therefore the median is visible in the middle value. But if it is even, therefore the median is the average of the two middle values. You need to add the two middle values and divide it by 2. You need to get the average. Let's take a look at the example. We have 5 data here, which means 5 is an odd number. Therefore, the median or the middle term of the 5 arranged numbers, 15, 67, 67, 68, and 75, the middle term is 67. 67.0. Therefore, the median is 67.0. So that is when the data is odd. If the data set is even, for example, with this example, we have 6 examples, 6 data. Therefore, we get the average of the two middle terms. And the two middle terms here are 67 and 68. Therefore, 67 and 68 divided by 2, the median is 67.5. Oh, that's easy. And I do believe you are following. And thank you so very much. Now, we have the mode. The mode is the most frequent value. It can be unimodal, bimodal, or multimodal. When we say unimodal, there is only one mode. Bimodal, there are 2 modes. And multimodal, there can be many, multiple modes. And for this example, we have the data 67, 15, 75, 68, and 67. Obviously, the mode is 67 because it is the only data which is repeated. And it is unimodal because we only have one mode, 67 only. Next, let's also talk about the shape. We are done with the center. CSS stands for center, the shape, and the last one will be discussed later. So we have CSS, center, and now we are on shape. Center shape. Let's talk about the shape. If mean is equal to the median or also equal to the mode, the shape of the distribution is symmetric and normal, or um, also called Gaussian curve, normal bell curve. So this is the normal distribution. It looks like a bell and it is symmetric if the mean, the median, and the mode are all equal. So with this example, the mean is 30, the median is 30, and the mode is 30. If mode and median is less than the mean, therefore the shape of the distribution trails to the right, and it is called positively skewed. Trails to the right, and it is called positively skewed. This means that from the mean, there are many more data that can be considered the mode and the median on the left side. So the the shape of the curve is not normal, it is positively skewed to the right. And if mean is less than the median and is still less than with the mode, the shape of the distribution trails to the left and considered negatively skewed. Negatively skewed. So the shape of the normal curve differs depending on the mean, the median, and the mode. This is called the skewness. How to compute for the skewness? I have presented here too many computation formula, but the first one is the most commonly used. We also have the Pearson's coefficient of skewness, Kelly's coefficient of skewness, Bowley's is coefficient of skewness, the moment base skewness coefficient of skewness. The formula for skewness is simply the summation or adding the mean and the sample summation of the difference of the mean and the sample mean raised to 3 or the cube all over the value of the standard deviation raised to 3. So these are the following formula. You may choose among these. And if there are questions, I would like to discuss this in other manner because we have limited time to explore all these computations. We also have when we talk about the shape in relation to spread, we have the so-called kurtosis. Kurtosis is presenting the bell curve with its shape and its spread. If the curve is clustered together and it is too high, therefore it is a positive kurtosis. If the curve is normal, it looks like the green one on this drawing, on this presentation. And if the curve is negative, they are more spread, the kurtosis is negative. We call the platykurtic or the negative kurtosis as platykurtic. It cluster less than the normal, flatter peak around the mean, and it has fat tails. So the red one on this presentation is the so-called platykurtic. It is more spread and it is less clustered. On the other hand, we have the leptokurtic. The leptokurtic cluster more than the normal, higher peak around the mean, and thin tails. So that is the blue one, the leptokurtic. And of course, the last one, the normal one, is the so-called mesokurtic. The mesokurtic is the black bell curve on this presentation. Now, question: why do we need to know the shape and spread? Why do we need to know if they are um, too dispersed or too spread, and if they are too clustered or too close to each other? Suppose we have scores of our students in our classroom, and the scores gather around 30 to 35 out of 50 test questions. So out of 50 test questions, the scores of the students are clustered around 30 to 35. If a student got a score of 2 and another one got a score of 49, they are so-called outliers now. Why? Because the normal scores of students are clustered around 30 to 35. However, there is a student who got a value of 2, a score of 2, and another student who got a score of 49. They are the so-called outliers, and there comes a question. A question to the teacher, to yourself, a reflection if I really did the right thing or possibly did the wrong thing. Why? What happened to this student who got 2 and to this student who got a 49 out of 50? On the other hand, if they are too spread, it will be alarming. If the scores of the students are spread from 2, 15, 21, 35, 37, and then 41, 49, 50, they go along the scores from 1 to 50, they are spread. The teacher should assess his himself or herself, because I think or she thinks she must have forgotten something, that maybe his teaching method or teaching style, or maybe his or her assessment does not fit to the objectives, or any form of reflection, so that we will be able to understand what is wrong and what is doing right and what is going wrong. So let's not be happy if the scores are too spread. Our aim with the statistics, with our lessons, with our as teachers, with our study, also with our researches, our aim is to see scores clustered together, close to each other. Because if they are too spread, that means there is something wrong, and we need to assess what is going on. So when we talk about spread, the last one, the spread, we have the range. Range is computed only by taking the maximum minus the minimum. Maximum minus minimum value. The second one is the variance. Variance is one of the most frequently used measures of spread. And these are the two formula for variance. We have the population variance and the sample variance. Again, I believe we will be talking about it in another seminar, or you may browse tutorials online. There are many of them, but it only tells us that this is the formula, and it's easy but rigorous to work on. The next one is aside from variance, the next one is the standard deviation. The standard deviation is the last and third among this measurement of spread. So this is the formula for population standard deviation and for sample standard deviation. It is only a square root of the variance. So if you already have taken the variance, therefore you already know the standard deviation. And again, let's not be happy if the standard deviation, the range, or the variance is too spread. Let's not be happy. Let's ask ourselves what is happening on our data if it is too spread. But if it is too close to each other, um, maybe there is a credibility on the scores, or reliability. So that is another point of discussion. I have taken this example from a very good statistician in our province and a researcher as well. May I acknowledge Sir Mark Rustum Valentin of Pada Pada High School. From his study, he presented Table 10, Descriptive Statistics of the Research Skills of the Grade 12 students. And I believe this is a winning research in our province. Let's take a look at this part. Standard deviation. Standard deviation before the use of spare kit is 0.911. 0.911, which means it's not even one, it's not even a whole number. Therefore, it's not, it is fairly dispersed, not too much dispersed. And it is a good value of standard deviation, a good number. When we say standard deviation, they should be close to each other. And the data should be close to each other. And the standard deviation after the use of spare kit is 0.760. Again, it is fairly dispersed, which is not often presented in a research. But Sir Marcus Tumbalintin have presented the standard deviation on his research, and we may also do that to show the world that the scores of the students, the scores of those who have taken your research, your study, um, is clustered, and they are reliable scores. There is credibility and reliability among the scores because it shows a very small amount of standard deviation. And I believe Sir Joshua Evaristo, my partner, has more to give. Let me end my discussion with this line: statistics is the grammar of science. As I've said earlier, statistics is not only about bunch of numbers and computations. In statistics, it's how you analyze and interpret the data. So it's a language. This is from Carl Pearson. Again, this is Warren V. Gragasin, and thank you for listening. Thank you. Later on, we will encourage you to ask questions. But for now, let's have the second speaker.
Thanks, Warren sir, for giving enlighten us with your pulse of wisdom and on probability and statistics. And probability is very important for our daily life because some it is some kinds of the prediction, and statistics is also the some data sample data collect proper data. So it is so important for our education and also the daily life. Thank you so much, sir, for your clear concept on probability and statistics. Thank you, sir. And it's time for move our next speaker. Our next speaker is Joshua
Thank you.
Lasinga.
Thank you very much for.
In between time, I want to remind you, don't forget to share, tag, mention your friends, community in comment box. If you will get the e-certificate link in the comment box and easily collect e-certificate from www.eduigp.com. Please give a warm welcome to our Joshua Lasinga sir. Hello sir.
Hello, sir. Hello, ma'am. Good evening.
Good
Good
evening sir.
morning.
So you
Can
can
I
continue.
start? Hello, ma'am.
Yes sir.
Can I present my presentation now?
Yes sir.
Thank you so much. Is my presentation already visible, ma'am?
Yes sir. It's visible.
Okay, thank you. Again, good morning, good afternoon, and good evening to our global audience. To each and everyone who are here in this webinar, I hope and pray that you are all doing great and safe. Before I begin my discussion, I would like to express my deepest thanks to all of the people behind this webinar. I'm truly grateful and blessed to be selected as one of the speakers for today's session and to be able to share what I know for today's topic, statistics and probability. First, to the Lord Almighty for the grace and blessing, to the Institute of Global Professions for providing us the platform for this session, to Dr. Nestor P. Nuesca, our mathematics supervisor in Region 3, Central Luzon, uh, to Dr. Ronaldo A. Pozon, a Schools Division Superintendent in the Schools Division of Tarlac Province for the trust and confidence, to Dr. Augusto L. Ballesteros, our ever supportive mathematics supervisor in the schools division of Tarlac Province, again, Philippines, to my mentor, Sir Redentor B. Tabamo, the head teacher 3 in Benigno Aquino, S. Aquino National High School, to our dynamic principal, Dr. Mariolito G. Magcalas at Capas National High School, together with together with my head teacher, Sir Manny L. Isip, at Capas National High School, to my friends, to my family, and my colleagues at Capas National High School for the love and support. Again, my name is Joshua Evaristo, a junior high school math teacher in the Philippines and a educational YouTube content creator. And I'm truly grateful and blessed to share my insights about probability. I hope by the session's end, you will gain something from me and from my discussion. So, since we only have limited time to discuss all the topics in probability, I chose some of the topics which I think are the most important topics that we need to familiarize ourselves. So we're going to talk about a little bit about the introduction to probability, the addition rules for probability, the multiplication rules for probability, combinations and permutations, random variables, probability distribution, normal random variables, and its probability distribution. So, without further ado, let's start. Let's begin by the definition of probability. So, when we say probability, it is a branch of mathematics that enables us to predict the occurrence of an event as a result of an experiment. So, some of the examples of experiment are tossing a coin, we have rolling a die, picking a marble in a jar, and choosing a card. So, these experiments are activities which could be repeated and they have a well-defined results. Meaning, these activities must have well-defined results. Okay, so the result of an experiment is what we call the outcomes. Let's have an example. In the our experiment is tossing a coin. If you toss a coin, the chance or the possible results could be a head and a tail. And the head and tail now is what we call the outcomes in the given experiment. Another term that we need to know is the sample space. So when we say sample space, that is the set of all the outcomes in an experiment. Okay, it's usually denoted by letter S and can be written using a set notation. So if we're going to get all the results of an experiment and uh, put it in a set, then that is the sample space. For example, like for example, in our example, the sample space could be the set of head and tail. Okay. Then we have the event, which is a subset of a sample space. The event came from the sample space. Okay, so an example of event is getting a head or getting a tail. Okay, for you to understand this, let's have an example. So a spinner wheel has three equal sectors colored green, orange, and blue. So what are the chances of landing on blue after spinning the spinner? Okay, so our experiment here is spinning the spinner. So the possible outcomes could be green, orange, and blue. Then the sample space are the set of green, orange, and blue. So based on the given problem, the event is landing on blue. Okay. Also, we have other examples of event. It could be landing on orange and landing on green. But for these specific problem, the event is landing on blue. Going back to the problem, since we only have a single event, that means this problem is an example of a probability of simple event. So we can solve it using the formula probability of event is equal to the number of event all over the number of sample space. Again, the number of event is 1, and that is uh, landing on blue, and we have 3 total sample spaces, which are the green, orange, and blue. So we have one third. In percentage, that is equal to 33.33%, because 1 divided by 3 is 0.3333. And if you're going to transform that into a percentage, it is 33.33%. Okay, let's have another example. A jar contains 7 green marbles, 5 red marbles, and 8 blue marbles. If a ball is picked from the jar, what is the probability of getting a blue marble? Okay, now, for this example, again, our sample space are the set of 7 green marbles, 5 red, and 8 blue marbles. So the formula is still the probability of event is equal to the number of ways the event can occur over the number of possible outcomes. So the number of ways the event can occur here is equal to 8, because we have 8 blue marbles. And the total number of marbles is 20, since 7 plus 5 plus 8 is equal to 20. We're going to simplify 8 over 20. We have 2 over 5, since we can divide the numerator and the denominator by 4. 8 divided by 4, we have 2. 20 divided by 4, we have 5. And 2 over 5 in percentage, that is 40%. Okay, so I believe that you already know how to transform fractions into percentage, fractions to decimals. If you forget, it's just simply 2 divided by 5, then you have 0.40, and you're going to move the decimal point. So we have 40%. Okay. So there are problems which consist of 2 or more events. Like for example, find the probability of getting a 6 and 1 when 2 dice are rolled. In this given example, we have 2 events, that is getting a 6 and getting a 1. So this is now a problem that can be solved using the probability of compound events. Okay, again, if we have 2 or more events, we have a compound events. If we only have a single event, that is simple events. Okay, so in order to answer this one, we have to determine first our sample space or the possible outcomes. So we have 2 dice, so we can show it using a table, like what you seen in the screen. So we have the first die, or the first column, are the possible outcomes for the first row, rather, are the possible outcomes for the first die. Then the first column determines the possible outcomes for the second die. Then we're going to combine the column and the row to determine all the possible outcomes, okay, in of the 2 dice. So the possible outcomes are the following. So the total possible outcomes, or the total number of sample space, is equal to 36. If you are just concerned to the total number of possible outcomes or the total number of sample space, you can use the fundamental counting principles, that is 6 times 6, because we have 6 possible outcomes for the first event, which is uh, the first die, and another 6 for the second die. So 6 times 6, we have 36. But I've shown you all the possible outcomes so that we can answer our second question. And that is, how many numbers of outcomes in the event? So we have 2. Okay. Why? Because we know that 6 and 1, when 2 dice are rolled, is an event which consists of 6 and 1, or 1 and 6. So we have 2. Okay? So now to determine the number, or to determine the probability of the event, which is getting a 6 and getting a 1, we have 2, which is the number of outcomes in the event, all over 36, the number of sample space. 2 over 36 can still be simplified. That is 1 over 18. Or in percentage, we have 5.56%. So we have 5.56% chances or of getting a 6 and 1 when the two dice are rolled. Okay, now we're done to the first uh, topic, and that is the introduction of a little bit introduction to probability. Let's now proceed to the addition rule. Okay, so when we use the conjunction uh, or in probability, that means addition. Again, in probability, when you hear the word or, that means addition, and we are referring to the union of two or more events. Okay, so however, the conjunction and means multiplication, and we are referring to the intersection of two or more events. So now let us discuss the first one, which is the addition rule for the probability before we proceed to the multiplication rule. Okay, so the probability of union of two events can be classified either the mutually exclusive event or the non-mutually exclusive event. The two events is said to be mutually exclusive if the two events have no outcomes in common. Another one, the two events cannot happen at the same time. This is also referred as the disjoint events and can be classified by two non-overlapping circles. Since event A here is completely different from event B. Again, that is mutually exclusive events. In mutually exclusive events, the formula that we're going to use is the probability of A or B is equal to the probability of A plus the probability of B. If you notice, we use the word or the conjunction or, and we use the operation addition. Okay, so that is the addition rule. So, in order for you to understand this, let's have an example. So, what is the probability of getting a 4 or face card in a deck of cards? So, again, we have two events, and the conjunction that we used for this specific problem is or, which means that we're going to use the addition rule. Okay. So, the first event is getting a 4, and another event is getting a face card. The possible outcomes for the event A are the 4 of clubs, the 4 of diamonds, the 4 of hearts, and the 4 of spades. However, on the getting a face cards, or the face cards are the jack, the queen, and the king of clubs, the jack, queen of king of hearts, the jack, queen, and king of diamonds, the jack, queen, and king of spades. So we have 12 possible. So we have 12 in the getting a face card. Okay. So as you can see, notice you can notice that all the possible outcomes on both events are different. Okay, so there's uh, no outcomes on both events are the same. Okay, so in that case, we are we're going to use the mutually exclusive events formula. Okay, this is an example of mutually exclusive event, just like what I've said a few minutes ago. When we say mutually exclusive events, the two events have no outcomes in common. So if we're going to illustrate it using two circles, the two circles are non-overlapping. Okay, so again, the formula. Okay, so we're going to find first the probability of getting a 4. So that is equal to 4 over 52. Why? Because we only have 4, 4 cards that contains 4. And the total number of cards in a deck is 52. Again, if we're going to find the probability of getting a face card, we have 12 over 52 because we have 12 numbers of face card and the total numbers of cards in a deck is 52. Okay, so to get the probability of getting a 4 or a face card, we're going to add the probability of getting a 4, which is 4 over 52, and the probability of getting a face card, which is 12 over 52. Okay, so remember the rule in adding fractions. Similar fractions, we're going to add the numerator, then copy the common denominator. So we have 16 over 52. If we're going to simplify it, we have 4 over 13. Since we can divide the numerator and the denominator by 4. If we're going to transform it into percentage, 4 over 13 is 30.77%. So based on the problem, we can say that there is a 30.77% chance to get a 4 or a face card in a deck of cards. Okay? So after we discuss the mutually exclusive events, let us now talk about the non-mutually exclusive events. So in non-mutually exclusive events, the two events have no outcome in common. The two events can happen at the same time, and it can also be referred as the joint events, wherein you can illustrate it using two overlapping circles, or we have a Venn diagram, wherein the overlapping region is the intersection of the two events. Okay, you can notice the sign that I've used. We have an inverted U. So that is the symbol for the intersection. And that is the part where the overlapping circles meet. Okay, so in non-mutually exclusive events, the probability of getting A or B is equal to the probability of A plus the probability of B minus the probability of A and B, wherein the probability of A and B is what we call the intersection, or the probability of A intersection B. Okay, so that is the difference between the mutually exclusive and non-mutually exclusive events, which are both under the addition rule for probability. Okay, so let's have an example. Suppose that we're going to get a card. So what is the probability of getting a diamond or a face card in a deck of cards? So again, the first event is getting a diamond. Then we have another event, and that is getting a face card. So the number of diamonds is 13. Since we have 13 cards, 13 diamond cards from A, 2, 3, 4, 5, 6, 7, 8, 9, 10, the Jack, the Queen, the King of Diamonds. On the other side, getting a face cards, we have 12. Okay, so we have the Jack, the Queen, and the King of Clubs, the Jack, Queen, and King of Diamonds, the Jack, Queen, and King of Spades, the Jack, Queen, and King of Hearts. Okay. This is an example of non-mutually exclusive event. Why? Because this is an example because you can notice that the two events have possible outcomes in common, and those are the Jack, the Queen, and the King of Diamonds. Okay? So those three cards can be put inside the overlapping region of the two circles, because those cards contains in the first event and on the second event. Okay, so to find the probability of getting a diamond or a face card, we're going to find first the probability of getting a diamond. So how many diamonds do we have in a deck of cards? How many cards? So we have 13. So we have 13 over 52. Why 52? Because the total number of sample spaces is 52. Because we have 52 total numbers of cards in a deck. Okay? So next, what is the probability of getting a face card? How many face card do we have? So we have 12. And again, and again, the total number of cards is 52. So we have 12 over 52. Okay? So in non-mutually exclusive event, we are also concerned to the probability of getting a diamond and face card, because the event A and the event B have something in common. There is an outcome. No, there is a there. We consider the probability of getting a diamond and a face card in this example, because this is an example of non-mutually exclusive event, because there are cards which are diamond, and at the same time it is a face card. So how many cards do we have? We have three, right? So we have the probability of getting a diamond and a face card is 3 over 52. Okay, so let's proceed. So using our formula, the probability of getting a diamond or a face card is equal to the probability of getting a diamond, 13 over 52, plus the probability of getting a face card, 12 over 52, minus the probability of getting a diamond and face card, or the intersection of the diamond and the face card, that is 3 over 52. If we're going to solve this, remember that when we add or subtract similar fractions, we're going to solve the numerator. So we have 13 plus 12 minus 3. Then we're just going to copy the same denominator. So we have 22 over 52. And again, we can still simplify it. So we have 11 over 26. In percentage, that is equal to 42.31%. Okay? Okay, so let's have another example. Okay, Sheldon rolled a fair die and wished to find the probability of the number that turns up is add or divisible by 5. So for this example, uh, to answer this, let us identify first the sample spaces. So in a die, we have six sample spaces, because we have there are six faces in a die, right? So we have one, the two, the three, four, five, and six. So the number of sample space is six. Then for the first event, that is getting an add number. So the add numbers from 1 to 6 are 1, 3, and 5. So we have 3. Okay. The second event, divisible by 5, we only have 1, because only the number 5 is divisible by 5 from 1 to 6. Okay. Now, let us consider uh, this, this question. So based on our discussion, can we consider this as a mutually exclusive event or non-mutually exclusive event? You may type in your answer to the comment box so that uh, let's see if you can get the correct answer. Okay, so the correct answer for this question is non-mutually exclusive. Why? Because there is an outcome that can be found on both events A and B, and that is 5. Okay, so in that case, we're going to concede, we're going to we're going to consider the intersection of A and B, or the probability of getting A and B, or what is common on both event A and B, and that is 5. So we're going to count the number of event A, we have 3, the number of event B, we have 1, the intersection of A and B is 1. Okay? To solve the probability of A or B, we have the probability of A So that is equal to 3 over 6 because we have three number of events in event A. Total number of event A is 3 all over the total number of sample space we have 6 plus the probability of B. How many events? So we have one event, okay, all over 6 because again, the total number of sample space is 6 minus the probability of A and B, that is also 1 over 6. Okay, so we can solve this one. 3 plus 1 minus 1, that is 3 over 6 or 1 half. In percentage, that is equal to 50%. Okay, so if Sheldon rolled a fair die and wished to find the probability of the number that turns up is add or divisible by 5, he has a 50% chances. Okay, at this moment, we will talk about the multiplication rule for probability. Since we're done discussing the addition rule for probability, let's proceed to the multiplication rule. And I will present the independent events and the dependent events. Okay, both of these events use the conjunction and and just like what I've said, when we use the conjunction and in probability, that means multiplication. Thus, the operation that we're going to use is multiplication. Okay. If the outcome of one event has no effect on the outcome of a second event, that is an example of independent events. However, if the outcome of one event has an effect on the outcome of a second event, then we can consider it as a dependent events. Okay? So again, when there's no effect, we have independent. When there's an effect, that is a dependent events. So the probability, since again, since we're talking about the multiplication rule, okay, so we will use the word the conjunction and the operation is multiplication. When we have an independent events, the formula is probability of A and B is equal to the probability of A times the probability of B, because the first event does not affect the second event. Okay. However, when we have a dependent events, the formula is different. The formula is probability of A and B is equal to the probability of A multiplied to the probability of B following A, because there is an effect. The outcome of the event of one event has an effect on the outcome of the second event, and we have to consider it. Okay, so that's the difference between these two, the independent events and the dependent events. If we have an example of problems about probability, multiplication probability, a rule for multiplication, uh, let you can look to these two words if there's any. If there's a replacement, we have an example of independent events. If we don't have any replacement, then that is an example of dependent events. Okay, so for you to understand the concept between these two, let's have an example. In tossing a coin and rolling a die, find the probability that a coin shows up head and a die shows up a 4. Okay. So what is the conjunction that we use? We use the conjunction and. Okay. So in that case, this is we're going to use multiplication rule, but we have to consider also if this is an example of independent or dependent events. Okay. So this is an example of what is this is an example of independent events. Okay, why? Because the probability of getting ahead in tossing a coin does not affect the probability of getting a 4 in rolling a die, because we have to experiment. And the first experiment does not affect the second experiment. In that case, our formula is very simple. We're going to use the formula for independent events. That's probability of A and B is equal to the probability of A multiplied by the probability of B. And what is the probability of A? The probability of A is 1/2. Why? Because we have uh, one, one head in a coin, and we have two possible outcomes. Those are head and tail. How about on the second one? Okay. For the second one, the probability of getting a probability of getting a 4 when a dice rolled is equal to 1 over 6. Why? Because we only have one uh, face of 4 in a die, and we have 6 total numbers of faces. Okay, so we have 1 over 6. And again, this is an example of independent events because the event A does not affect the event B. Okay, so if we're going to multiply 1/2 by 1/6, we have 1 over 12. The rule in multiplying fractions, that's numerator to numerator, denominator multiply to the denominator. And 1 over 12 is 8.33% in percentage. Okay? I hope that you are learning. Uh, so let's proceed to the next example. The two cards are drawn from a deck of 52 cards. Find the probability of getting a 4 and a face card. If the first card is not replaced in the deck before the second card is drawn. This is an example of dependent events because there is no replacement. Then the outcome of one event influences the outcome of the second event. Okay. Again, when there's no replacement, we have an example of dependent events. Okay. So without replacement, the keywords is card is not replaced. Okay. So in that case, since this is an example of dependent events, the probability of getting A and B is equal to the probability of A times the probability of B following A. And what is the probability of getting an A? Or the probability of getting a 4? The probability of getting a 4 is 4 over 52. Why? Because we have 4 cards. Okay, the 4 of diamonds, the 4 of hearts, the 4 of spades, the 4 of clubs. Okay, suppose that we pick the 4 of clubs. Okay, since we pick a card, then we pick another card. Okay, so suppose that we pick the 4 of clubs. Now, what is now the probability of getting a face card? Okay, so how many face card again do we have in a deck of cards? We have 12. So we have 12 face cards over the total number of cards. We have 51. Why 51? Because we already picked a card a while ago. And that is the probability of getting a 4, which is the 4 of clubs. Okay, then we the card is not replaced. Therefore, we're going to subtract 1 to the total number of cards, which is 52. Okay, so in order to solve this, again, numerator to numerator, denominator to denominator, that's 48 over 2,652. And if we're going to simplify, we have 4 over 221, since we can divide the numerator and the denominator by, so that is 12. Okay, so 4 over 221, that is 8.33%. So you can see that we have only 8.33% chance uh, to get 4 and a face card in a standard deck of cards without replacement. Okay? So another example, okay, so the box contains 6 apples and 4 pineapples. Then Dominic randomly chooses one piece of fruit, eats it, and chooses another piece of fruit. What is the probability of he choose an apple then a pineapple? So based on the problem, we're going to look for a keywords to identify if this is an example of independent or dependent events. Can you determine if this is an example of independent or dependent events? Okay, so I'm going to give you 5 seconds. Okay, so if your answer is dependent events, then you are correct. And the keywords are eats it and chooses another piece. Okay, without even mentioning that there is a replacement. Therefore, this is so we don't have any replacement. Okay. So the probability of getting an A and B is equal to the probability of A times the probability of B following A. Okay? So that because that is the formula that we're going to use when it comes to dependent events. Okay, so what is the probability of getting an A or the probability of getting an apple? So we have 6 over 10. How about the probability of getting a pineapple? We have 4 over 9. Again, there is no replacement. So we're going to subtract 1 to 10. So we have 9. Okay? So if we're going to solve this, we have 24 over 90 or 4 over 15. Since we can divide the numerator and denominator by 12. Okay, so if we're going to convert 4 over 15 in percentage, we have, okay, so you're going to convert it in percentage. So what is 4 divided by 15? So we have 26.67%. Okay. Okay. Now we're done discussing the introduction to probability, a short introduction to probability, the addition rule, the multiplication rule. Let's now proceed to the permutation. Let's talk about permutation. What is permutation? Okay. So when we say permutation, this refers to the different possible arrangements of a set of objects. The order of the arrangements of an object is very important. So when we say permutation, we are talking about the arrangement. The key word is arrangement. Okay. So how many ways can you arrange an object? Okay. So if that's the question, then we are referring to the permutation of an event. Okay. So we are also going to discuss combination, which is the opposite of permutation. Okay. Later on. Okay, so in permutation, ABCD is not the same as BCDA. Okay, ABCD is considered as one permutation. Then BCDA, we have another one. Okay, so because we're talking about arrangement, and arrangement is very important. Okay, when it comes to permutation. So for tonight or for today, okay, in other country, we're going to solve the different problems involving permutation, which could be in the form of permutation of objects taken all at a time, taken R at a time, the circular permutation, and even the distinguishable permutation. Okay, so let us differentiate between the permutation of uh, events taken all at a time and taken R at a time. Okay, so in this case, all of the objects are included in the arrangement. So that is taken all at a time. So when we say there are n objects, there are if we say taken R at a time, meaning not all of the objects are included. Okay, so if we're going to illustrate the first permutation of objects, we have the permutation of n comma n. Because we have the total number of objects is n, and we're going to take them all. Okay, so n comma n. Unlike on the second one, we can illustrate it using the permutation of n comma r, because we have uh, n is the number of the n is the total number of objects, and we're taking r at a time. Okay, so not all are included in the arrangement. And remember that r is less than n. Okay, so the formula for taken all the time, that is simply n factorial, then taken r at a time, we have n factorial all over the quantity n minus r quantity factorial. These two are example of linear permutation. Okay, how about the next type of permutation? We have the circular permutation. When we say circular permutation, these are the permutations of objects which they can be arranged in a circular pattern. So an example of this is the seating arrangement of students in a circular table. So the first two are an example of linear permutation, and the third one is an example of circular permutation. In that case, the formula is also different. Okay, so the formula that we're going to use is simply permutation is equal to the quantity n minus 1 quantity factorial, wherein n is the number of object. Okay, and the last example of the last kind of permutation that I'm going to discuss is uh, is the permutation where some of the objects are alike. And that is an example of distinguishable permutation. So when we say distinguishable permutation, this is a permutation of n objects when P are alike, Q are alike, R are alike, and so on. Okay, so for this kind of permutation, some of the objects are alike. Okay, so if we're going to solve for the probability of a distinguishable permutation, we can use this formula. Okay, the permutation is equal to n factorial all over p factorial times q factorial times r factorial, and so on. In other books, that is different, but the way you solve it is still the same. Okay, so the variables uh, are not the same, but the way you solve it is still the same. Okay, so in order for you to understand the difference between the four types of permutation or kinds of permutation, let's have an example. Okay, so for the first example, in how many ways can 12 people occupy 12 seats in front row of a mini theater? So this is an example of permutation of objects taken all at a time, because we have 12 people and we're going to arrange them all. So again, the formula is the permutation of n comma n is equal to n factorial, wherein n here is the total number of objects. So how many people do we have? We have 12. So that is 12 factorial. And we know that 12 factorial is simply 12 times 11 times 10 times 9 until 1. Okay? So 12 times 11 times 10 times 9 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that is equal to 479,001,600 ways. But you can skip actually the third line. If you're going to use calculator, you're just going to type 12, then you're going to look for the factorial sign, then press it, then press enter. Then the answer is 479,001,600, and that's already the final answer. Okay, let's have another example. Suppose that there are 8 basketball teams competing for the top 4 standing in order to move up to the semifinals. Find the number of possible rankings of the 4 top teams. So this is an example of permutation of n objects taken r at a time. because we have 8 basketball teams and we're just concerned for the top four standing. Okay, so the possible rank of the top four teams. Okay, so we have n is equal to 8 and r is equal to 4 because we have 8 basketball teams and four. We're going to take in four at a time. Okay, so the formula n factorial all over the quantity n minus r quantity factorial. You're going to substitute the value of n and the value of r. Then you're going to solve. When we solve, we have to use the Pemdas rule or the Pemdas rule. If you can still recall, uh, it means that we're going to start solving inside the parentheses. And 8 minus 4 is simply 4 factorial or 4. Then we're going to copy factorial. Then we're going to expand 8 factorial. It can be written in the form of 8 times 7 times 6 times 5 times 4 factorial. Okay, so we can divide now the 4 factorial. We can cancel now the 4 factorial because it is written on the numerator and on the denominator. Okay, that means that is equal to 1. Then 8 times 7 times 6 times 5, if you're going to compute it, we have 1,680. So therefore, we have 1,680 possible ranking. Okay? Okay, so we're going to proceed to our next example. So for this example, okay, as you can see, there is a ring. Okay, so how many ways can 8 children join hands to form a ring? So what do you think is the kind of permutation that we're going to use for this example? What kind of permutation? Okay, for this example, we're going to use circular. Okay, circular permutation because of the keywords form a ring. Okay, just like a circular table. Okay, so the formula quantity n minus 1 quantity factorial, then substitute n, which is equal to 8. 8 minus 1, that's 7 factorial. So what is 7 factorial? That is simply 5,040. If you're going to solve by getting the product of 7, 6, 5, 4, 3, 2, and 1. So the answer for this specific question is 5,040 ways. Okay, let us now proceed to our last example for permutation. Then we can proceed to our next uh, topic. So the question is, how many distinguishable permutations are possible with all the letters of the word assessment? Okay, so we are concerned with all the possible, with all the, we're concerned to all the, we are concerned to the number of arrangements, okay, we have in the word assessment. Okay, so this is an example of distinguishable permutation because in the word assessment, in the word assessment, S comes 4 times and E comes 2 times, meaning that there are objects there are objects that are alike. Okay, so in the word assessment, we have 4S and we have 2E. Okay, so if we're going to use our formula, that is simply n factorial all over p factorial times q factorial times r factorial and so on. So what is our n? Our n is the total number of letters in the word assessment, and that is 10. So we have 10 factorial. How about the p, the q, and the r? So the p, the q, and the r represent the letters which are alike. Okay, so we have 4s, so we have 4 factorial. We have 2e, so we have 2 factorial. In other books or in other references, they include 1 factorial intended for a. 1 factorial for m, 1 factorial for n, and also 1 factorial for t. But remember but remember 1 factorial is only 1. Okay? If we're going to include it, it is still the same. Okay? So since we know that if you're going to multiply any number by 1, the answer is still the number. So for me, it is better not to write 1 factorial anymore. Okay, it's simply 10 factorial all over 4 factorial times 2 factorial. Okay, so if you're going to compute 10 factorial, we have 3,628,800. The 4 factorial is 24, then 2 factorial is 2. Okay, then we are going to simplify the denominator and divide it. So the total numbers of distinguishable permutations we have is 75,600. Okay. Okay. After we discuss permutation, let us now discuss combination. Just like what I've said, combinations is the opposite of the permutation. When it comes to combination, it is the number of ways of selecting from a set when the order is not important. The key word here is selecting. Okay, unlike for the permutation, it's all about arrangement. Okay, you are concerned on how many ways can you arrange specific objects. Okay, for a combination, in how many ways can you select, can you choose. Okay, if that is the case, if you're going to select few objects, or if you're going to choose only few objects, then you are not concerned to the order of the object. So therefore, in combination, ABC, BCA, CAB, ACB, BAC, CBA is just one combination. Okay? If you can recall, if this is permutation, we have 6 permutation. But the order here is not important. That's why it's combination. Therefore, we only have one combination. Okay. So we have here two formulae to the of combinations. The first one is the combinations with repetition and combinations without repetition. Again, if you're going to answer a problem about combinations, make sure that you can understand, you comprehend the the problem. You have to know if the the problem is about combinations with repetition, or it is a problem about combinations without repetition. Later on, I'm going to elaborate the difference between the two by giving you an example. Okay, so these are the formula. The first formula is combination of n comma r is equal to the quantity of n plus r minus 1 quantity factorial all over r factorial times quantity n minus 1 quantity factorial. On the other side, without repetition, that's simply n factorial all over r factorial times n minus r quantity factorial. Okay? So let us proceed in the given example. Okay. So the first example, there are 44 there are 44 politicians at the gathering. They shake hands everyone. How many handshakes were there? So this problem is all about handshakes. Okay? Imagine that the politician A, okay, the first politician shake hands to the politician B. Does it make any difference if the politician B shake hands to the politician A? Okay, the answer is no, because that is just one handshake. Okay? If that is just one handshake, therefore, that is an example of combination because the order does not matter. Okay, we only have one handshake. Okay, if the politician A shake hand to the politician B, or the politician B shake hands to the politician A. Now, the second question is this an example of a combination with repetition or without a repetition. Okay, so in this example, we have a combination without repetition since a person cannot be chosen twice. Okay, you have to shake hand to other person. Okay, so in order to have one handshake, so we're going to use the formula for the combination of n comma r is equal to n factorial all over r factorial times the quantity n minus r quantity factorial. After writing the formula, simply substitute the given values. And what is our n? Our n is 44 because we have 44 politicians. Okay, what is our r? Our r is 2. Okay, why? Because in every handshake, there are two people involved. Okay, so r is equal to 2. After you substitute the given values, we can now solve. And by solving, you again don't forget to use the PEMDAS or the GEMDAS rule, because if we're not going to follow it, our answer is will not be correct. Our answer is not correct, or there is a possibility or the probability, big probability that our answer is wrong. Okay, so we have 44 factorial all over 2 factorial, then 44 minus 2, that's 42 factorial. Okay, then we have 44 times 43 all over 2 factorial. Because we cancel here the 42 factorial found on the numerator and denominator. Because we can write 44 factorial in the form of 44 times 43 times 42 factorial. Okay, that's the reason why there is no 42 factorial on the third line. Okay, so the last one, we have 44 times 43, 1892 divided by 2 factorial. That is simply 946. So in this case, we have 946 total number of handshakes. Okay. Okay, let's say that let's have another example. Okay, so for this example, it says that we have 6 flavors of ice cream. The first one is banana, the lemon, the melon, the chocolate, vanilla, strawberry. So we can have 3 scoops. How many variations will there be? Okay, so let us uh, let us use the letters for the flavors. We have B for banana, M for lemon, melon, L, C, V, and S. Okay. So if we're talking about variations, we're talking about uh, different selections of flavors. No. So since this is so we have an examples of let's have an example of selections. Let's say we have CCC, or 3 scoops of chocolates, or we can also have BLV, or one scoop for banana, lemon, and vanilla. You can also choose BLL, or 1 banana and 2 lemon. Okay, since this problem is more on selection, then this is about combination. Okay, so the keyword is selection. So how many variations do we have? So we have that is our question. Okay, since we are concerned about the selection, we're going to apply combination. And again, we still need to know if this is an example of combination with repetition or without repetition. So we're going to look at the examples here. Since you can notice that there is a repetition. For example, you can choose chocolate 3 times, okay? Or you can choose 2 lemon, okay, for the third example. So that means this is a problem about combination with repetition. In that case, what we're going to use is the formula intended for combination with repetition. And that is the first one. Okay? So again, you're just going you have to write first the formula, then you're going to substitute. That's very simple. You just have to know what is our n and what is our r. Okay, what is our n? Our n is 6. Why? Because we have 6 total number of flavors. And what is our r? We have 3 because we're going to we have to we need 3 scoops. Okay? So let's try to solve this. 6 plus 3 minus 1. You have 8. Then 6 minus 1, that's 5. Okay? So we're going to uh, simplify this one. Okay? The numerator, it can be written in the form of 8 times 7 times 6 times 5 factorial. So we can cancel 5 factorial on the numerator and on the denominator. Okay? So 8 times 7 times 6, that is 336. 3 factorial is 6 because 3 times 2 is 3 times 2 times 1 is 6. Then, if we're going to get the quotient of 336 and 6, we have 56 variations, total number of variations. Okay, so let us now proceed to our next topic, which is the random variables. So what is random variables? When we say random variables, these are the variables that assumes the number of values that is derived from the outcome of an experiment. A random variable. This is different from the variables that we are using in algebra. Okay, random variable is more on probability. Okay, so given for example, we have the random variable x, the number of times that the coin turns up tail in tossing coin 5 times. Random variable y, the sum of two numbers in rolling two dice, wherein the resulting variables will then be from 2 to 12. Why? Because when you roll a die, the minimum number of value is 1, right? So if the first die that comes up a 1 and another die comes up 1, so 1 plus 1, we have 2. Okay, also for the maximum, the maximum, we have 6. Then 6 plus 6, we have 12. And we have also the random variable z, the total distance traveled by a taxi cab in a week. These are just examples, few examples. So we can create our own random variable. Okay, so a random variable can be classified either discrete random variables or continuous random variables. So according to the values it assumes. Okay, for the discrete, if it is countable, then we have discrete random variable. If it is uncountable, then we have a continuous random variable. Okay, for in our examples, x and y are random variable x and y are both examples of discrete random variables. Uh, on the other side, the random variable z is an example of continuous random variable because we are talking about distance. And when we talk about distance, the possible outcomes are uncountably infinite. Okay, so it's not an integer. Okay, that is a shortcut. If we can write it in an integer, we have countable, we can count it, right? So that's countable, so meaning we have discrete. Otherwise it is continuous. Let us try to answer the problem about discrete random variables. So 3 coins are tossed. List down all the possible outcomes and the values of the random variable y, representing the number of heads that occurs. Okay, so let us try to create our table with 2 columns. The first column represent the possible outcome when you toss 3 coins. So if you can still recall how to find the possible outcomes of tossing a coin 3 times, you can use either the table or the tree diagram. Okay, you can use the tree diagram. That's the most that is the simplest and my favorite when it comes to uh, when it comes to um, finding the all the possible outcomes in a given experiment. So these are the possible outcomes of the three coins tossed. Okay, so we have head, 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 tail, head, tail, head, tail, head, 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 tail, 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 head, tail, tail, head, and the tail, tail, tail. So on the other side, or the next column, we have the number of tails. So we're just going to count. So head, 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 we have zero. So head, head, tail, we have one. Head, tail, head, we have one. So we have one, then we have two for head, tail, tail. We also have two for tail, head, tail. Then tail, tail, head, we have two, and we have three for the tail, tail, head. Okay, so um, after we discuss discrete random variables, let us proceed to the discrete probability distribution. So what is discrete probability distribution? It is an organized tabulation or graph formula that lists the values of the discrete random variable together with their corresponding probabilities. Okay, so we can use or in probabilities, it involves the probability distribution of a discrete random variable that can be determined either the theoretical probability or the experimental probability. Okay, the experimental probability is also known as the observational or the empirical probability. I'm not going to elaborate this anymore since it's okay, our time is limited. So maybe in another webinar or another topic, okay, we can uh, discuss this one. Okay, so let us proceed to the uh, discrete random after we discuss the probability distribution table, the discrete probability distribution. Let us now determine when is discrete probability distribution valid or considered as a valid discrete probability distribution. We have to consider, we need to consider two things. The first one, the probability that each event in the sample space must be between 0 to 1. Okay, so 0 here means impossible, then 1 means certain. So all the probabilities of each event must be between 0 to 1. And the other one is the sum of the probabilities of all the events in the sample space must be equal to 1. If you're going to add all the probabilities of each event, it should be 1. Okay, a total of 100%. Okay, so those are the two things that we need to consider in order for our discrete probability distribution to become valid. Okay, let's consider this one. This is a table of discrete probability distribution, and we have to find the value of n. Okay, by just using the two two things that we need to consider in order for discrete probability distribution to become valid, we're going to add all the probabilities or the sum of the probabilities, which is 0.125 plus 0.175, 0.150, 0.200, 0.100. So if we're going to get the sum of these probabilities, we have 0.7 75 hundredths. I yes, 75 hundredths. Okay, so since the sum of the probabilities must be equal to 1 according uh, to the properties of discrete random variable, so we're going to subtract 1 to 0.775 hundredths, and that is 0.25 hundredths, or that is 25%. So the value of n here is 25%. Okay, so given the same table, let us now try to answer what is the probability that the random variable x is less than 0. So what are the random variable x less than 0? We have negative 10 and negative 20, the negative numbers. So all we have to do is to add 0.125 and 0.175. So we have 0.3. Okay, in percentage, that is 30%. Okay. So after we discuss the discrete probability distribution, let's proceed to the mean of a discrete random variable. So what is the mean of a discrete random variable? So yeah. Okay. So the mean or the expected value of x is given by the summation of the random variable x to its probability distribution. The mu, okay, the mu represent the mean. Okay, the Greek letter m, the Greek letter mu, sorry, represent the mean, and that is the expected value. And if you're going to find that, if we want to solve that, you're going to use this formula. Okay. So let's have an example problem about this one. So a car insurance company offers to pay 300,000 pesos if a car is stolen or is destroyed beyond repair. The insurance policy costs 25,000 pesos, and the company research shows that the probability that the company will need to pay the amount of insurance is 0.003. Find the expected value of the insurance to car owners. Okay. To let X represented the value of the insurance from the perspective of the car owners. Now, if a car is stolen or destroyed beyond repair or completely, then its value is represented by the insurance minus the insurance policy amount. So the insurance is 300,000 pesos minus the insurance policy amount, which is 25,000. So we're going to subtract it. We have 275,000, okay, pesos. However, during the entire life of the policy, a car owner did not meet such incident. Okay, so in that case, the value of the insurance is negative. Now we have negative 25,000 pesos because the insurance policy costs 25,000 pesos. Okay? So we have two random variables here. So we can now construct our probability distribution. The probability of the probability of negative 25,000 is now 0.997. So the given is only the random variable x, which is 275,000 pesos. The probability is 0.03, 0.003. So in order for you to solve the probability of negative 25,000, you're going to subtract 1 from 0. Okay. Oh, 0.020 again, 1 to 0.03. 0.003. Okay, that's 0.997 or 99.7%. So what is x times p of x? Okay, you're going to multiply 275,000 by 0.003, that's 825. Then negative 25,000 by 0.09 0.997, that's negative 24,925. Then you're going to add the 2. So we have negative 24,100. So that the expected value here is negative 24,100. So if we have negative, that means that the policy is designed to the advantage of the insurance company. So the advantage is to the insurance company because our expected value is negative. Okay? Okay, after we discuss the discrete random variable, let's now focus on our last topic, that is the approach on how we can solve the problems about continuous random variable. When we say continuous random variable, we are also referring to the normal random variable. We already know that the normal distribution is a bell-shaped curve, which is already discussed by Sir Warren. It is also known as the Gaussian distribution, since the Gaussian distribution or the bell curve, okay, And we also know that the probability distribution is the area under the probability distribution is equal to 1. Okay, so the probability x will fall in a particular interval. For example, we have let's say we have a and b. Okay, that is the shaded area in the in our presentation. So we can say that the probability of x is equal to a is equal to 0 for continuous random variable. Also, the probability of x is equal to b is equal to 0. If you're going to look at uh, the the graph, okay, of the graph, you can notice that you may notice that uh, we have an imaginary line here. Okay, so which means that the probability of x is equal to a or x is equal to b is equal to 0 for continuous random variables only, which implies that the probability of x greater than or equal to a is equal to the probability of x greater than a. Okay, or the probability of x less than or equal to a is also the same with the probability of x less than a. Okay. So the graph of a normal distribution depends on the two factors, the mean and the standard deviation. You can get the area under the normal curve by just no by no by only knowing the mean or the standard deviation. If you know the mean and you know the standard deviation, you can already get the area under the normal curve. Okay. So the mean determines the location, while on the other the mean determines the location and the distribution is a mirror image on the other side. Okay, that is the characteristic of a normal distribution. And when it comes to the measures of central tendency, the mean, the median, and the mode, they are all equal. Okay, so regardless of the mean and the standard deviation, the normal curve confirms the empirical rule. So we have an empirical rule that we have an empirical rule that we need to follow. Okay, that means we have 68% uh, area under the normal curve falls falls within the first standard deviation, then 95% within the second standard deviation, 99.7% on the third within the third standard deviation. And a trivia, uh, the normal curve will never touch the x-axis. Okay, that's continuous. Okay, okay. So we're going to use now the standardization to solve the probability of a normal random variable. So we have the standard normal random variable z, or it is sometimes called the z-score. It is defined as z is equal to x minus mu all over the standard deviation. Okay, or it is equivalent to x is equal to mu plus z, or the z-score times the standard deviation. So these are the formula that we're going to use uh, for the to solve the probability of a normal random variable, okay, or the continuous random variable. Let us try to have an example about uh, the probability of a normal random variable. So the question is, the average salary of a teacher is 29,900. If the average salaries are normally distributed with a standard deviation of 2,000 pesos, find the probability of a teacher makes less than 28,000 pesos. This is just an example. It's not true data. Okay? So this question or this problem can be illustrated of using the normal curve with the mean of 29,900. As you can see, the mean is located uh, on the middle portion of the normal curve. Then we have the 28,000 pesos that is on the left side of the mean. Okay, so since we are looking for the probability less than 2, okay, Less than 28,000 pesos. 28,000 pesos. Let's try to solve first the z-score. The z-score is equal to x. What is our x? The x is 28,000. Then what is our mean? The mean is, or the average. The average is 29,900 all over the standard deviation, which is 2,000. So if we're going to solve it, we have negative 0.95. Okay, by just using calculator or by solving it manually, that is our answer. Okay, negative 0.95. Okay, so since we're looking for the probability less than 28,000 pesos, so we were going to solve the probability of a normal random variable z less than negative 0.95, and that is the shaded part. Okay, when we say less than, it means this part. If we are concerned greater than the other part. Okay, so using the cumulative, there are two ways on how we can solve this one. The probability of the normal random variable z less than negative 0.95. The first one is by using the cumulative distribution table for a normal random variable, or also known as the z-score table. So the probability of z is less than negative 0.95 is 0.1711. If you don't know how to locate or find the specific value using z-score table, first you're going to look on the row side. Then we have to find the tenths value. So we have negative 0.9. Okay, negative 0.9. Then to find the hundreds value, we have 0.05. So negative 0.9 and 0.05. We have negative one. We have 0.1711. So therefore, the we have 17.11%. The shaded part is 17.11%. So aside from using the table of cumulative frequency, cumulative distribution, of a standard normal curve, a modern way to compute this is through the use of the computing program Excel. Okay, so if we're going to use Excel, Microsoft Excel, this is very simple. You are going to input only the following syntax. So first, you're going to type equal, then norm dot s dot dist, then open parentheses, then we're going to type the z-score, which is negative 0.95. Be careful. If it's positive, you write positive. If there is a negative sign, you have to write negative. Okay? Then comma, true. Okay? You have to choose true because you want to find the cumulative distribution function. Okay? And not the probability density function. Okay? So if you're going to enter that one, the result is 0.171056. Okay? So that is approximately 17.11%. So the answer is still the same. Okay? So in the problem, we can now conclude that the probability of a teacher makes less than 28,000 pesos is 17.11%. Okay. So that ends my uh, talk or presentation about probability. Okay, so I'm not going to elaborate all of the topics in probability because it's almost time, and I hope that you learned something from me and from my discussion. Thank you so much.
Thanks sir, for sharing your intelligible knowledge with us. I think our audience got your answer.
Thank you, ma'am. Thank you.
Yeah, audience, it's time for ending our session, our webinar. Today's webinar is so much informative and also our speaker shared so much knowledge for with us.
Good morning, dear learners and our speakers. First of all, our speakers, thank you so much for your beautiful presentation and knowledgeable presentation. Thank you, sir. See you. Definitely see you again. And today it's almost late night. It's 11:20 there. So today we don't have any quiz competition and Q&A. We'll directly move for the certification process. But in our side, we have some network difficulties. So today we just announced the code for certification. For today's code 2020 IGP 2020. For today's certification code IGP 2020. Next morning we will announce the certification link and code also in our comments in our Facebook page and group. Because right now in our office we don't have any internet connection. That is power interruption actually. So I'm just moderating this from my mobile, and I'm outside of office right now. So today we are not able to show the screen share to you. But for today's the certification code is IGP 2020. IGP 2020. Yes. And again, thank you, Sir Warren and Sir Joshua. See you again. Definitely see you again in the next part.
Thank you so much, sir.
Thank you, sir. Thank you. See you again. And today's certification code again IGP 2020. Thank you so much. See you again tomorrow.